Hello everybody to today's Basics of Life video, and today's topic is water. You can see the drop of water on the right hand side, and on the left hand side the three-dimensional structure of a water molecule. So the oxygen is in the middle, and in each corner of a tetrahedron there's either a hydrogen or a double electron. The overview of this video is, first we talk a little bit about water. What is it? How is it? And then why is water important for life? I don't have many definitive answers on that. Water in the solar system, and we definitely will have to discuss the snow line in the solar system, and then we are ready to answer the question, or try to answer the question, how did water come to Earth? And we'll also look at other watery worlds very shortly. Water is an anorganic, so-called universal solvent. I didn't understand that quite well, because water is polar, as we will see, and polar solvents solve certain things better than others. And then there are apolar and semipolar solvents. And the semipolar ones, I think, solve more things than water actually. But water does it in a way that is good for life, as we will see in a short time. It is a polar molecule with strong hydrogen bonding, and this hydrogen bonding, so from these are the hydrogens, they bond to the hydrogens of other molecules. This explains some of the features that water has, some of the very interesting features. One very special feature is that solid water is less dense than fluid water, which means that ice swims on water. It can be called water anomaly, but it's very practical for the fish and all the animals in the water, because if water was freezing from below, they would all die. But it makes a solid layer on top of the lakes, on the rivers, and swims, which keeps the water below warm enough for animals to spend the winter. Water has a very high specific heat, which also comes in handy, as we will see. And its tripole point is close to Earth's average temperature and average surface pressure. Here we can see the tripole point. The tripole point means at the tripole point you can have gaseous water, liquid water, and solid water at the same time. That's why water can make these fascinating clouds and things. Some are crystals, some are little droplets, some are larger droplets. You can see the shiny effects of the sun and the moon through that. Fascinating how water works. I think no other chemical can do that. Then on the Earth, 96.5% of the water is found in oceans, which means it is salty water. 1.7% is in glaciers, which means it's salt less. And 1.7% is groundwater, which will become sources. And only 0.001% is found in clouds. So even if we think clouds can rain a lot, most water is not in clouds. And in the Earth, the water's mass is 0.04% of the Earth's mass, which is, if you think about it, quite a lot of water. So you could cover the whole Earth with 3.2 kilometers of water. And this is enough water. We will never run out of water on the Earth. We may run out of fresh water and saltless water, but in total there's just a lot of water on the Earth. What's the importance of water and for life? People say follow the water and you're gonna find life, which may be a bit too simplistic, but practically speaking, it's a good idea to look for water. Water is important for the transport of soft molecules, and very importantly, as I told in an earlier video, it helps to build membranes. And this is the thing I mentioned on an earlier slide. Membranes consist of two layers, and one side of the layer is water loving, one side is water hating, and then the water loving side goes towards the water, and this makes the membranes. And membranes, as I told you in this earlier video, they can be cut, and what happens when you cut them is they make two smaller three-dimensional structures. So out of a sphere, if you cut it, you will have two smaller spheres. So you have organelles already, and you can have different chemicals and different organelles, and this comes in very handy for life. So you can have subsystems in a system made by the membranes. Then water is also very important for temperature regulation. On the Earth, this was a very important factor in the last 4-point-something billion years. And it can keep ecosystems stable. So as long as you have water somewhere, the temperature will stay within limits. And if the water level goes down too much in the summer, temperatures will just go up and up, which is not good for many plants and animals. Then we do a short tour through the solar system, or through the inner solar system. Which planets have how much water? For Mercury and also for the Moon, I just wrote some because it's not much. In both bodies, you can find it close to the pole as ice and in no other form. Not in liquid form because there is no atmospheric pressure, and not in gaseous form either, unless something hits the ice. And on Venus, that's one of the big question marks, why Venus has so little water. In the past, it had some 3 meters or something, or at least 3 meters, but the water went away, and now there's only 200 milligram water per kilogram atmosphere. So a kilogram is a cubic meter. On the Earth would be a cubic meter. On Venus, of course, it's less than that. But just 200 milligrams of water. And this is ultimately the reason for the hot climate on Venus, because had Venus had more water, it could have solved the CO2, and then the CO2 wouldn't make such a thick atmosphere, and the greenhouse effect wouldn't be as extreme. The Earth, as we have discussed already, has a lot of water, 3,200 meters or something, mainly in the oceans. Mars has had a 500 meters water layer in the past. Now it may be down to, say, 11 meters or something. So compared to the Earth, very little water, mostly on the poles. And I think it's a bit asymmetric. And one pole has more water than the other pole, which is probably due to Mars being asymmetric. It has this pear shape, and so one hemisphere is larger than the other, which has influence on the atmospheric pressure. Then, if we go out in the solar system, we can't talk much about the huge planets because we can't see into them. But for the moons, they tend to have quite a bit of water, especially the moon Europa, which has twice as much water than Earth, despite being smaller than the Earth. So you could cover it with 5 to 100 kilometers of water. And it's mainly in a liquid ocean under the icy crust. Then there's Enceladus, a moon of Saturn, which has 10 to the 10th cubic meter of water, which corresponds to a thickness of between 5 and 25 kilometers. So maybe the ocean on Enceladus doesn't go around the planet fully as possible. In some places it's thinner, in some places it's thicker, but it's still quite a lot of water. So basically, the more out you go, the more water you will find. But of course, it's cold out there. Then something we have to discuss, and discuss it at the example of the solar system, is the snow line. The solar system formed out of the rests of the protosun, and there are two lines, a silicate line and a water line. And the water couldn't stay in the inner solar system because the sun is very hot and cooked it away. So most of the water was found outside where Jupiter, Saturn, Uranus, Neptune are, or even further than that. Then some of the materials spiraled inward. The planetesimals, they spiraled inward as long as there were many of them, because each planet collected up material and was braked a little bit, and whenever they break, they go inside. So they were just hindered in the revolution by the clouds, especially Jupiter, that came inside quite a bit. So, and the dust drifted inward more strongly than the volatiles. That's what explains the silicate, that the silicate is more inside and the water is more outside. That's why the inner planets have lots of stone, and the outer planets, some of them, it's not even clear if they have a core, silicate core or iron core or not, but they have lots of volatiles. Another slide to the discussion of the snow line. Much of this work has been done by Morbidelli et al. With the development of the solar system. First you had these two lines, silicate line and snow line. The sun would be here. silicon line inside and the snow line where the sun has pushed the water out. But then it became more complicated because there were planets. And the snow line came a little bit inward because the planetesimals took the water with it, especially frozen water. So the snow line wandered a little bit towards the sun. But then what happened? Jupiter formed, and Jupiter is huge, so Jupiter collected up almost all the water coming inside from further away, whereas the silicate still moved inward. So we call Jupiter a filter because it filters the materials coming into the inner solar system. This is important for a discussion later. The discussion we're having right now. How did the water come on Earth? There are basically two theories, and we can't tell yet which one is correct. The one was the primordial water remaining on the Earth. But we know that the Earth was very hot. So even if it had a lot of water in the beginning, it may have cooked it off. But we will talk about a version of this later, because water could have chemically synthesized on the Earth once it was a bit colder and still had a lot of volcanism. Could it have come to us? First, people always thought about comets, because Whipple called comets dirty snowballs. Some are rather snowy dirt balls and don't have as much water as we have seen, for example, with comet Churyumov-Gerasimenko, which didn't have much water. But you can tell this also if you observe comets from the Earth. You can tell some have more of a plasma tail and some have more of a dust tail. And there are some comets that have almost exclusively a dust tail. Probably most are somewhere in between. But if you're walking on a comet, probably you see some streaks of ice, but most of the surface is dark with gravel. Then people thought asteroids, planetoids, could have brought the water. And there are arguments for that, as we will see on the next slide. But I still have doubts, because asteroids don't have as much mass, and some do not even have lots of ice. There could also have planetesimals going inside, but there's also a bit of a problem with that, which is this filtering I mentioned. The planetesimals had problems bypassing Jupiter and reaching the Earth. And the other thing is, when the moon was built by this Theia impactor running into the Earth, it could have left some water on the Earth if it was very water rich, which we don't know. Theia is hypothetical. Nobody has seen Theia, and it was completely destroyed, so that's why we can't see it. We will talk a little bit later about these two sorts of theories. The question, will the water stay with us? I already shortly mentioned that. The Earth loses a little bit of water. So per second it loses 27 kilos. the whole Earth, which is not much. It comes to about 855,000 tons a year. And if I calculated that correctly, it would be enough for 10 to the 12th years. So much longer than the sun is going to stay with us. So the water is not going away. But of course, it could be subducted and go into the Earth. We don't know about that, but definitely the Earth will never be a bone dry, waterless planet. This loss rate, of course, is calculated with the momentary loss rate. We don't know what happened if the ozone layer was destroyed. Then more ultraviolet would come and would split up more water in the atmosphere. So then the hydrogen goes away, the oxygen will stay. So this rate could also be considerably higher once the ozone layer is gone. Then something I already mentioned a little bit, water can be, the origin of the water can roughly be estimated from its deuterium to hydrogen ratio. Deuterium is called heavy water. There is water that has a neutron in the core. There is also water that has 2 neutrons in the core, which is called tritium. But heavy water is water with 1 neutron. And this ratio is very low. It's thousandths of or less, which is interesting for the people who want to make fusion of hydrogen, because deuterium is better than normal hydrogen. And there you can see this ratio is very much the same for the Earth and the asteroids. It will probably also be very similar for planetesimals that come where the asteroids are. But the further out you go, the stranger this ratio is. For the big planets it goes down, and for the comets it goes up. And Jupiter family comets have a more similar D to H ratio than the comets coming from the Oort cloud, which says something about their place of origin. But it's, of course, it's not only place of origin, but it's also how much water was lost. Because if you cook away the water, more of the normal water will leave than of the deuterium water. So probably on Venus you still have more deuterium water in relation to normal water than on the Earth. By the way, the interstellar comet Atlas has a very high T to H ratio, which people say has to do with coming from somewhere else. Other watery worlds are, for example, K2-18b. We discussed this in an earlier video about life. And Kepler 138c and D, maybe also E if E exists. Then this Gliese 9827d and the TOI 1452b. These can be categorized into 3 types: ocean worlds, Hycean planets, and steam worlds. Hycean planets are planets with a hydrogen atmosphere but water on the surface. And the steam worlds, as we will see, they are very common. And practically all of these 4 are steam worlds. For K2-18b, in these plots from the NASA webpage, we always see the habitable zone as a green belt. and K218b is right inside this belt, so probably the water will be cooked away. So it's tends to be a steamy planet. These Kepler, C and D, and probably also E, if it exists, they're also well inside the habitable zone of this little star Kepler 138. So also there on the hot side, and maybe not so good for life because it's too hot. Then the J9827d is even more extreme. So you can see at the very periphery of the image, you can see the habitable zone quite far away. The other thing that's obviously discussed is that the planets close to the star tend to have synchronized rotation. And people think it may not be too good because on one side of the planet it's very hot and on the other side very cold. But if you have enough atmosphere, for example, like on Venus, the night side is not much colder than the day side. It's not strictly always an argument. Then the last example is the TOI 1452b. As we can see, also super Earth, so a planet that is larger than Earth. It has 5 Earth masses. And they talk a lot about Star Wars with this planet because it goes around 2 suns. Actually, there are 2 ways of circling around 2 stars. Either you're very close to one star or you're very much outside both stars. Otherwise, you run into problems and maybe expunged. So a stable orbit can be done only very close to one star or very far from both stars. And here again we say it's inside the habitable zone. Why is that? Are there only watery planets that are close to the stars? No, probably not. This is probably an artifact of the easier detection of close nearby stars with most methods to detect planets around foreign other stars, unfortunately. But of course people want to find a planet that is similar to the Earth, which one day we'll find because methods are improving. It's a funny planet, that one. As a takeaway, water could have been built on the Earth, but it could have also brought back to the inner solar system, and maybe it was a little bit of both. But the question is why does the Earth have so much water, and why does Venus have so little water? And Mars is probably somewhere in between. And not probably, Mars is somewhere in between. On the Earth, water is almost permanently recycled, unless just these 27 kilos per second that are going away. Water is widely found, not only in the solar system, but also in the universe. I haven't shown you that here, but of course you can measure it with spectroscopy, infrared spectroscopy in protoplanetary disks and in the atmosphere of planets. Many models of the development of life see water as important. For example, the watery pond models, or also the black and white smokers models, which often work in a sulfury environment of volcanism. Could a similar molecule have given rise to life, for example with CO2 or the carbon world and the organic world made out of carbon. People have discussed, could you change carbon with silicium? Up to a certain degree, yes, but you couldn't make proteins out of silicium, I don't think. And if you change one atom out of water, for example, sulfur, instead of oxygen, you get a very poisonous molecule that is not even closely similar to water. So probably water can't be replaced very easily by other frequent atoms found in space. And H2S doesn't have the same features as water. For example, the forces between the molecules are very different. Sulfur is also special, but special in a different way because it bonds very strongly, but too strongly. So the topic of water, we just touched it a little bit, but there's a much more to say to that than I actually did. But it's just my momentary knowledge about the importance of water for life in space. So stay curious and hope you have a nice time.